Hello guys, so we are going to continue our discussion with respect to the transformers. So this is the first topic that we are going to pick up and we are going to understand. So here I've also given the definition, so that is the reason I've written what and why in transformers. So if you really just want to understand a simple definition about this particular architecture, it is nothing but in transformers in natural language processing are a type of deep learning model that uses self-attention mechanism. Please keep a note of this because this is really important. To analyze and process natural language data, they are encoder-decoder model that can be used for many applications, including machine learning translation. Now, if I talk about machine learning translation, this is specifically something called as sequence-to-sequence task, right? Now, when we say sequence-to-sequence tasks, let's say I want to solve a problem statement. One of the example that we can probably take is like language translation, right? Language translation. And if you probably go ahead and see an example of Google Translate, right? This is a task of sequence to sequence task. It is a sequence to sequence task because if I really want to convert from English to French, right? English to French. So in this scenario, you'll be able to see that my input with respect to English will be many words. I will be having many inputs over here. It will be many, and my output will also be consisting of many words. So this basically becomes like a many to many sequence to sequence task, right? Now, when we have the sequence to sequence task, and obviously length of the sentences is also a meaningful thing over here, right? Length of the sentence. Now, as the length of the sentences increases, we should be able to solve this particular problem again with a very good accuracy. So in this kind of task, usually transformers is used, okay? But you may be thinking, Krish, fine, you have also told that in the previous architecture of encoder-decoder, you told that this is also used for sequence to sequence task. And if I talk about encoder and decoder, like they were, if I just probably go ahead with this particular diagram. So I had an encoder over here, right? And I had a decoder over here, right? So in encoder and decoder, what we used to do, we had our LSTM right over here, and based on this LSTM, when we used to go ahead and pass this entire sentences, okay. Please remember, we do not take the output in this, right? So if I just go ahead with a basic architecture of encoder decoder, you'll be able to see that if I used to give my words over here, let's say x1, x2, x3. And this words we used to give based on timestamps. T is equal to 1, T is equal to 2, T is equal to 3. So let's say if this is my sentence 1, which is having this particular words. And again, we used to convert this entire words by using some embedding layer. Okay. Convert this into vectors. Okay. And then pass it to the entire LSTM. So this was my LSTM over here, right? And this is my encoder and this is my decoder, right? So after doing this, finally, you should see that we were able to generate one C vector, that is context vector, right? So here I will just go ahead and generate this context vector. And based on this context vector, we used to provide it to our next decoder layer, right? Next decoder layer, which used to have this LSTM, okay? So here is my decoder completely. I will pass it over here. And then with respect to this particular decoder, I used to also get my output, and here we used to use some kind of softmax, right? Now, this was the basic architecture of the encoder decoder, right? And this is what we used to do. This context usually used to define when we are passing every words based on the timestamp, the final context that we used to get at the end of this particular sentence used to represent this entire sentence itself, right? Which is consisting of this entire words. And this context was further sent to our decoder model. And this decoder model would use to do the prediction based on this context that we have. And along with that, we used to also calculate the loss. Everything was discussed, right? Based on the encoder architecture. But one problem we understood from the encoder decoder was that this context was not sufficient to represent this entire sentence if the sentence length increases. If this increases, the C context was not at all sufficient, right? And this was the problem with respect to the encoder decoder architecture. And that is the reason you could see that our blue score was decreasing as the length of the sentences was increasing. So this I've covered in my previous video. I would suggest if you want to quickly revise it, you can go ahead and do the revision. Okay. Now, for this, we also had seen an architecture. So here was my sequence to sequence learning. This was the entire research paper of this, how the entire working actually happens. Each and everything was explained clearly over here, right? So after this, what we did is that in order to solve this problem of the context that we had, like our main idea was that, okay, we should not create the entire context at once and probably send it to the decoder model. Instead, what we can actually do is that we can use something called as attention mechanism. And that is where this research paper came, right? So based on this research paper, what we exactly did was that the plan was very simple. Instead of just giving a single context, we had to actually provide an additional context to our decoder. And this was the architecture we specifically discussed about. And if you remember in our previous videos, we have discussed the entire mechanism, now how this attention mechanism actually works, right? And we discussed about this entire research paper over here. So here was the entire working, wherein along with a single context, we also have to provide additional context, create our alignment scores, create our attention weights, and then pass it to the decoder. Okay. And that is what we specifically solved it with the help of attention mechanism. So let me do one thing. Let me just take this screenshot. Okay. So that you will be able to see this reference over here. So here I will just put this reference, and here also I have added this additional reference. So this was all possible because of your, the attention mechanism, right? So this is the entire working, right? And with the help of this, what we were able to do is that we are able to provide additional context to the decoders. And then this decoders, what they were able to do is that they were able to do the prediction, and the problem with respect to the long sentences, right? The problem of accuracy that we are facing, it started increasing, right? Because of this research paper. But still, let's understand with this attention mechanism. Okay. So here we are using bidirectional LSTM RNN. Here also we are using LSTM itself. One problem that we see with this attention mechanism or encoder decoder, okay, attention mechanism or encoder decoder, is that we pass every words based on timestamp, right? So here parallelly we cannot send all the words in a sentence, right? And again, because of this, see, over here you'll be able to see even in encoder decoder, we used to send the words based on timestamp, right? Now, when we are sending the based on timestamp, at t is equal to 1, I'm sending one word, t is equal to 2, I'm sending another word, right? Similarly, over here in this bidirectional LSTM also, I'm sending one word at a various timestamp. We won't be able to do the entire execution or this entire training parallelly, right? And because of this, yet your attention model is not scalable. When I say scalable, that basically means if my data set is huge, right? Still, the encoder decoder attention mechanism will not be scalable with respect to training. And this is really important to understand, because the new models that we'll be seeing with respect to transformers uses something called as, they never use this LSTM RNN in encoders or decoder, right? What they use is that they use this something called as self-attention module. And because of this self-attention module, you'll be able to see that all the words will be parallelly sent to the encoder for further processing, right? And that is what this architecture comes into existence. See over here in the input embeddings, right? You're sending all the input all at once. So it is supporting this entire parallel execution. And that is where, because of this, we'll also be learning about one more topic, which is called as positional encoding. Positional encoding. We'll discuss about this as we go ahead, right? And this will also play a very important role for this when we are sending all these words parallelly, and how each and every word vectors is going to get computed. We'll discuss about this. What exactly this self-attention module will be doing, we'll be discussing about it, right? Now, you should definitely understand over here is that in attention mechanism in encoder and decoder, we are not able to do this. Hence the word scalable. Now, when we say scalable, that basically means why these transformers are really performing well is that as we keep on increasing the data set, you'll be able to see that we are able to get some amazing models, amazing state-of-the-art models. I'll say SOTA models, right? So state-of-art models we will be able to get specifically with respect to NLP task. Now, this is not just restricted to NLP task. With the help of transfer learning, right? With the help of transfer learning. Now, transformers are even used in multimodal. Okay, they are used in multimodal tasks. Multimodal task basically means task that has both NLP plus image. So here also they are able to perform really, really well. Okay, how it is able to perform and all, we will understand once we understand the entire architecture. But this is the major important thing that you really need to understand. Why transformers? What was the problem that we had in our previous models like encoder, decoder and all? And this is one of the very important problems that we have, right? So just defining all these things, since it solves all these problems, you'll be able to see now everywhere this entire transformers have really changed the AI space. Now you'll be able to see a lot of SOTA models, right? And this SOTA models is nothing like, let's say, some of the transform models that we have, which is already trained in huge data set, is like BERT, GPT, right? Now, what companies are doing, if they really want to create their own model, they don't have to train it from scratch. And these models are trained with huge data, right? They can directly just use transfer learning. And with the help of this transfer learning, they are creating this amazing SOTA models, right? State-of-the-art models, right? And the architecture, this is completely based on transformers itself. And as I said, multimodal task, the same architecture is also used with respect to images. So if you see in OpenAI, some of the application like DALL-E, right? They actually just based on a text, they are able to generate the images, right? Entirely, it is completely based on transformers. So just to give you an idea, this will also be very much important because based on this architectures, various LLM models are also used in generative AI. Okay, generative AI. LLM basically means large language models. So I hope you got an idea. Just take this into consideration. This is a very important thing that we have discussed. Parallelly, we cannot send all the words in a sentence in attention mechanism or encoder or decoder. But with the help of transformers, we are not at all using LSTM RNA. Instead, we are using self-attention module. And this self-attention module functionality will be that we will be able to send all the words, right, parallelly for the further processing. What exactly happens in this self-attention module, we'll discuss more about it. Okay. So I hope you got an idea about this. One more very important problem that we see in transformers, that is with respect to contextual embedding. Contextual embeddings, right? Now, what exactly happens in contextual embedding? We will discuss about this. Okay. Now, with respect to the contextual embedding, let me just give you an example in order to make you understand this. Okay. Let's say I have a sentence. My name is Krish and I play cricket. Okay. Now let's say over here, when I pass this entire information, right, in my embedding layer, let's say this is my embedding layer. Now, in embedding layer, when we pass it, our main task will be that from this embedding layer, for every word, we should be able to get our vectors, right? Some vectors. So if I pass my, then name, I should be getting another vector. Is, I should be getting another vector. Crush, I should be getting another vector, and I should be getting another vector. Based on timestamps, I will be getting this kind of vectors. And understand, if you are specifically using embedding layer, and let's say if this embedding layer is using some word embedding techniques like word2vec, for every word, we are going to get a fixed vector. Okay. So this, if my is there, then I will be getting a fixed vector of some dimensions. Similarly, name is there, I will be getting a fixed vector. Okay. Is there, I will be getting a fixed vector. Krish is there, I'll be getting a fixed vector. And is there, I'll be getting a fixed vector. I will is there, I'll be getting a fixed vector. Right. And similarly, play is there, I'll be getting a kind of vectors itself. Right. All these words will be represented in some kind of vectors. Now, I need to make you understand about contextual vectors. What exactly is this contextual vectors? See, it is always a good idea that if you are able to get a vector, it is fine, right, for every word. But we should always try to get a vector whenever we have a longer sentences based on the relationship with other words. Now here you can see my name is Krish and I play cricket. Okay. I is obviously related to Krish. There are some kind of relationship, right? So if I probably give this same word on my contextual vector embedding, vector embedding, then all the vectors that I will be getting, this vector should be having some kind of relationship with respect to the other words. Like Krish and I, here there is a very strong correlation, right? So some context will be there. I play cricket, so cricket is also there. So this cricket vector, I should not be getting a fixed vector itself. I should be getting a vector which should be related to Krish. Based on this particular relation, there should be some changes in this particular vector which suggest that, hey, there is some contextual dependency in this particular word, right? And this entire problem is solved by our self-attention. And because of this, you'll be able to see that our transformers will be damn more accurate, right? And we'll be talking more about this self-attention module in the upcoming video. But if I talk with respect to the most two overall problems, why transformers are specifically used. One is, here in transformers, parallelly we can send all the words for processing, because of which it makes the entire model scalable with respect to training with huge data sets. Okay. The second thing is that it has this contextual embedding thing, right? Which was basically missing in encoder and decoder. Because in encoder and decoder, we just used to use an embedding layer. We used to pass each and every word, get a vector, and further do the processing with respect to this. But now with the help of this self-attention, you'll be seeing that we'll be able to even create contextual vector embedding. Now in our next video, we are going to deep dive more into this and try to understand how this entire architecture basically works, and step by step we'll try to get each and everything as we go ahead, right? So yes, this was it from my side. I will see you all in the next video. Thank you.